Hey guys, so in the last lecture, you started a new chapter that is economic analysis. So, in that chapter, you've seen introduction to economic analysis, that why an economic analysis is required, why it is the crux of the renewable energy sources, because it should be economically viable to compete with their conventional source of energy. That is the reason it becomes very much important. Then we have seen few cost, that is initial cost, and then we have seen annual cost. Then we have seen few definitions, that is annual savings, cumulative savings, life cycle savings, and payback period. Then we started with some calculations, and first was present worth calculation. Sorry, present worth calculation. So what is present worth calculation? So it is the current value of a future sum of money. Current value of a future sum of money, of cash flows. So what is the that is the present worth calculation. So suppose the present worth of a rupee needed n years from today is given by, means suppose you are having 100 rupees today, then what it's worth after 10 years. So it will be, suppose, be 160. So that is the present worth of your money today. So what will be the after 10 years of your 100 rupees today, so that how much worth it is your present, so that need to be calculated. So for that, the formula is given, that is 1 upon 1 plus d raised to n. So we have seen that sum sum of sum of the present worths, all the sum of the present worths is given by sigma 1 to n aj upon 1 plus d j. So here, what is a and d? So a are the payments that are due for first year, second year, and n years. So how much payments you are doing. And what is d? D is a discount rate. A is payments and d is discount rate. So this, from this we will get sum, and this 1 plus d raised to j is called present worth factor. So this term we are calling as PWF. So we have seen that sum is equal to sigma 1 to n aj into PWF, present worth factor. So there is a relation between all the successive payments from the initial payment. So that is, the aj will be equal to 1 plus I raised to j minus 1. So here, instead of aj, we are going to write a1 into 1 plus I raised to j minus 1. So this is the formula for sum. So this we will use in one of the examples. And if I is equal to d, if I is equal to d, that is interest and discounts are same, then the sum will be a1 into 1 plus I upon j minus 1 upon 1 plus I upon j. So it will be 1 a1 into n upon 1 plus I. So this is the formula when I is equal to d. So these formulas we will use in example. So now the next topic is, that is repayment of loans in equal installments in EMIs. So how we can repayment the loans in equal EMIs. So that we are going to study. So suppose let the initial investment required for system is taken as C. So C is initial investment, and fraction F1 of this amount is taken as a loan. So F1 is taken as a loan. Then let the lending institution charges an interest rate at D1. So D1 is the interest rate. So the loan is to be paid back in equal installments of A. So A is EMI for a period of n years. Taking the value of each annual repayments at the time of making initial investment. Now here this is equated monthly installment, but we are considering as yearly installment. So we can write it as equated yearly installment. So now the formula. So here F1 is loan fraction. So this will be around, so this value will be around in percentage, that is 60 percentage, 50 percentage, or something percentage of initial investment. So how much loan has been taken? So the loan has been taken is, that is F1, that is 50 percentage or 60 percentage of initial cost. So this is the loan amount. And now we will use the formula of sum of words, sum of present words, that is sigma, running from 1 to n into a upon 1 plus d 1 raised to j. So let's, so now if we expand this term, then it will become that is a into the bracket, it is 1 upon d1 minus 1 upon d1 into 1 plus d1 into n1, then plus extra terms which we can neglect. So our formula will become a upon d1, we are taking as common, so that is 1 minus 1 upon d1 into 1 plus d1 raised to n1. So this is our formula for the amount of loan which we have taken. So now we want to find EMI, that is how much amount we need to pay every month or every year. So that is the A. So A we need to find, so we will make A as a subject. So A will be equal to D1 F1 into C divided by 1 minus 1 upon D1, sorry, D1 has been taken as constant, so here there's a mistake, so here D1 will not come, so it will be 1 upon 1 minus 1 plus D1 raised to N1. So this is the formula for equated uh, installment, how much installment you need to pay. So this formula we will also use in examples to find the EMI or yearly. Then the next, so the next topic is fuel savings. Fuel no, sorry, annual savings. That annually how much money has been saved. So let us consider a renewable energy system. Similarly, as you discussed in last, it requires a total investment of C, of which the fraction has been taken as a loan. Fraction total investment. The interest rate is D1. Then it is to pay back in a period of equal annual installments over a period of N1 years. So if we assume the annual load to be met to be E, E is the annual load to be met, and renewable energy supplies a fraction of this load. If it is supplying the fraction of its load, the rest being supplied by the auxiliary system. So this would result in annual savings of F into E. So F into E will be your annual savings. This will be annual savings of conventional energy unit. So take this cost of this energy. If CF is the unit of per energy, is the unit cost of per energy, and it increases the rate of energy by IF year. So if it is increasing by IF year, raise in cost, so the annual expenditure, so how much savings will happen, so savings, so the annual expenditure required this by the system is by the way of electrical energy, running subsidiary equipments, maintenance and local taxes. So take M as a cost associated with these minor items. In the first year it increases, so suppose M is the minor cost, then IM is the rate at which it increases. Then finally, it is assumed that the tax deductions are allowed. So tax deductions are allowed both on the interest component as well as annual repayment installments as well on the depreciation of the system. So depreciation is assumed to be at uniform rate, that is RD. So this is the depreciation rate, and the income tax rate. This is the depreciation and income tax rate RF. rate. So in any year J, so savings of the fuel of electricity will be CF, that is unit cost, how much cost it is saved, into 1 plus IF. This is a raise in that cost. If the cost is being raised to J, raised to J minus 1. So what is J? So any year, so suppose fourth year, so how much electricity is being saved? So this is the formula. This is generally the formula for compound interest. So the compound interest formula has been used to find the compound savings. So annual repayment on loan. So how much repayment on loan has to be done? So the repayment will be D1 F1 C, as we have seen in the last topic, that is this formula D1 F1 C upon 1 minus 1 plus D1 raised to N1. So that formula I'm going to write here again. So D1 F1 C upon 1 minus 1 upon 1 plus D1 raised to N1. So this is the annual savings. So So this is the savings, but now we need to deduct the other costs. So for deducting other costs, so other costs will be electricity, sorry, will be electricity bill for the subsidiary equipments plus maintenance charges plus local taxes. So this we are considering as M into, that is minor cost, this all plus 1 plus I m raised to j minus 1. Similarly, we have used again the compound interest formula for considering the other costs. So tax deduction on the interest component of loan repayment. So how much tax will be deducted? So so what will be our total savings now? So the total savings will be equal to, so how much savings we have done? So savings is CF into 1 plus IF raised to j minus 1. So that is our total savings. So that is CF into 1 plus IF raised to j minus 1 into F into E. So what is F into E? So as we know that F is annual annual load, that is F is fraction and E is the load. So into F into E, how much load it is saving, and minus will be annual repayment of the loan. So this is the repayment every year that we are doing, so this term will subtract. So that is D1 F1C upon 1 minus 1 upon 1 plus D1 raised to N1. So this is the total savings, that is how much saved minus how much you are paying back uh, to the EMI for installing that equipment. So this is the total saving, annual saving. So this also will use in the example. So in the next lecture we will see cumulative savings and payback period. So as we will solve examples, these concepts will be more clearer, that how this calculations has to be done. So this is some somewhat derivation theoretical part. So we will see examples also from next lectures. So Thank you very much.